Hello, everyone, and welcome to this exciting session about our TechTalks series. Today we are we have invited Cameron Coyle from VoxelJet. He will be presenting in the webinar titled 3D Design Printing: Challenges, Innovation, and Technological Advancements. He's Senior Sales Manager at VoxelJet, which is one of our partners. The presentation will delve into the world of 3D design printing, focusing mostly on challenges associated with this manufacturing method, present innovation enabled full-scale production, and the technological advancements pushing the boundaries of what is possible. Additionally, will be explore real-world application and some case studies of how 3D design printing can optimize production processes, offering tangible benefits across various industries. Before we begin, let's remind some quick webinar rules. So we will have open all the webinar, the Q&A button section. So if you have any question, please write down in this section. Okay. We will have 5 minutes at the end of the webinar to reply to all your questions. So please feel free to write everything. If we don't have enough time at the end, please write us back later on, or when we thank you for participating, please remind us that we couldn't reply it. Thank you again for joining us. Let's give a warm welcome to Cameron from VoxelJet. And I think the stage is yours.
Amazing. Thank you very much, Angelica. So good afternoon also from my side. As Angelica mentioned, here today for the TechTalks webinar to present a little bit about 3D sand printing, some of the challenges, innovations and advancements that have been made in this space. So today I hope to give you just a brief introduction to myself, also talk about the company and 3D sand printing as a process. We will cover some of the challenges to using 3D sand printing before taking a look into some of the innovations for production, and then also some advancements with the technology, which is entering us into some new markets. So as Angelica mentioned, I'm one of the senior sales managers at VoxelJet. I actually joined in 2016, and today I'm responsible for the UK, Scandinavian and South American markets. And my focus really is to support customers to take advantage of the 3D printing technology, implement it into their business, into their foundry, and learn how to take advantage of that technology to create some more value for their end customers, or it could be to also solve some problems which they have in the foundry. So briefly, just to cover VoxelJet as a company. So some of you may have heard of us before. We've been around since 1999, and today we are a global 3D printing company with 4 locations. The headquarters is based in Germany, where we hold all of the R&D, the assembly, and our service center also to supply customers with the 3D printed parts. And then we also have facilities in the US, India, and China. So we're not a huge company. We have more than 250 employees. Oh, jump back. 250 employees globally. But we have a large support from our sales partners throughout the world to support the customers in various markets. Just to touch a little bit about the business model from VoxelJet, we split the business into 2 segments. One is for services and the other is for systems. On our services side of the business, we work with customers to support and introduce the technology through our on-demand printing centers. And this is where we can supply customers with one-off parts or production volume parts. Then on the other side, we can also offer a variety of 3D printing systems for those companies who wish to bring that technology in-house. We're working with the customers with the adoption cycle, where customers will take the printed parts in-house to learn and develop and grow before building up their usage to justify a 3D printer in-house. In some cases, customers continue to use the support from our service center, even if they have a machine in-house, for maybe some special projects or larger components, or if they have not enough capacity from their current machine due to the work that they gain. With the 3D sand printing and dealing with the foundries, we are of course into many different industries. When the company started, of course, the first customers were often the German automotive OEMs, such as BMW, VW. But over the years, we've then grown into other areas, including aerospace. So these are, let's say, the two main markets that started in the very beginning, where today we're now looking into agricultural, oil and gas, nuclear, lots of art projects, or also marine projects. So we've really diversified a lot as the foundries become familiar with the technology and also are able to implement it. What we also see is that parts are becoming more complex. If we have some foundries in the call today, you may also see this from your end customers. And this is also driving a transition into the 3D printing. So to speak a little bit just about the binder jetting process. So binder jetting is the method which we use to 3D print these sand components. And it all starts with a CAD file where the machine then takes that data and slices it into a 2D bitmap layer. Then the actual printing process will start. And in VoxelJet's case, we are always using powder-based technology. So we have the recoating method, which is the first step of the printing here, where we apply a layer of the sand onto the build platform. Then we move to step 2, where we have a print head, which will selectively dose a binder where you would like to create your component. And then the whole build platform will either move down or move up, depending on the machine, to create space for the next layer to be created. This process is then repeated, or these 4 processes are repeated until you have a complete job box of printed parts, where you can then move to an area where you unpack the parts, which is where you remove them from the surrounding sand. And then you are using compressed air to blast away any remaining sand stuck to the part before you have your finished component. And the process in this way offers a lot of flexibility in the design of the castings and also the sand molds or cores, because you're not constrained by traditional means. And that could be draft angles or assembly methods in where you have to assemble them all together. So you can start to print components as single pieces for cores, for example. And this can really take advantage of the technology and simplify the manufacturing process. So now we can take a short look into some of the challenges which we see for using 3D sand printing. I've highlighted 4 here, but as you can see, there are many other challenges which we could also speak about. And some of those challenges to using the technology also apply to traditional methods. But the 4 which we would focus on today would be the cleaning of parts. This is particularly important when you're 3D printing something which has a high complexity. Also the price, surface of the component and accuracy. And then a big topic which we often talk about is gas issues created during casting, where we hope to try and solve some of those problems with 3D sand printing. So first, we can take a quick look into some of the challenges and how we solve them in relation to the surface accuracy and gassing. And we can combat some of these problems by offering different binders, and then also different sand types. So on the screen now, you see two binder options. One is a furan binder, and the second is a phenolic binder. And with these processes, we can use a variety of sands. Here we have the GS14 and GS19 sands. These are both silica sands. And then we also have some special sands such as ceramide. So depending on the sand which you use, you can have effects onto the surface quality of the casting, how it's performing during casting with thermal resistance, and then also the gas which is created or allowing the gas to escape through gas permeability. If we speak about the GS14 sand, this is the most common sand which we use for 3D printing. It offers a average grain size of 140 microns, and it's printed with a 0.3 millimeter layer. It's particularly good for aluminium castings, for molds and cores, and it can be then used to produce a better surface finish in comparison to some of the other sands. Next, we would have the GS19 sand. This could be used for a casting where you would like to have a better gas permeability of the printed part, to allow that gas to escape during casting, but it would offer a slightly rougher surface finish because it's a 190 micron average grain size. Then we would have a ceramide sand. This is a man-made spherical bead sand, which allows you to produce components with a very high thermal resistance, which is particularly good for example, a steel casting or a core for a steel casting. The ceramides can also help, ceramides and bauxite, sorry, can also help with sand burn-in, because of the temperature resistance that the sand brings to the printed part. As I said, very similar to some of the challenges which you face in traditional casting. So just as a short scale, you can see here that as you move through the sands, you have your surface finish will become rougher, but your gas permeability will increase. And as I mentioned, that's directly linked to the grain size of the sand which you are using. We use, for example, on iron castings for some quite large pieces, quite often a GS19 sand, where we then can get the gas permeability, and with some coating, they can get some resistance to the sand burning of that part. So here we can take a short look at a customer case study of a printed part which we worked on in the past. This is a aluminium foundry based in the UK. They're called BCP, or Brooks Crownhill Pattern Makers. And this particular part is an EV motor core. It's 350 by 300 by 275 millimeters and around 10 kilos as it stands today. And through this project with the customer, we worked with them for around 2 months to test and validate the process and different design ideas in order to solve some of the problems that they were having. When the customer came to us, they actually first came with only the water jacket as a single core and not all of these additional features which you see today. Now, when they had this first just the water jacket version, it creates a very fragile core. We have to send that from Germany to the UK, and also it made it quite difficult to handle that part and ensure that it arrives in a good condition. So we worked with that customer, and this was linked to the price challenge that we had, to add in some more features to the core to add some more value, and then also simplify the pattern equipment, which would also help with their price. So in this case, now we have the water jacket. The water jacket will port at 4 areas. You can see 2 marked here, and then you have the internal cylindrical core also included. So everything comes as a single package, and that allows the customer to take what was previously a very complex and difficult to handle part, and make it very easy to handle in the foundry, at the same time as lowering their pattern equipment costs. If we speak about the surface accuracy and gassing issues, when we first started this project, we worked with the customer and we used a silica sand. And what we found was that it was, let's say, instead of creating a circular shape, it was creating an oval shape during casting. So the silica sand expansion was sort of affecting the dimensional accuracy. And they were also getting some very small micro gassing at the surface of the casting in between these two areas. So as a result, we looked into some of the different sands which we offer. And in the end, we concluded with a furan binder with a ceramide sand. So the ceramide in this case gave them a very good gas permeability, but also a good stability of the core during casting, which created this accuracy which they saw, and allowed them to produce the parts as intended. Now we can take a short look into a steel casting. This is actually also a UK foundry called Brave Engineering. This time we have a very large core for a steel casting in a nuclear application. So you see here it's a 815 millimeter diameter core, and it weighs about 130 kilos. So very, very big. And the challenges again we had here was about gassing and also the surface finish. Gassing because the core is surrounded by such a huge amount of metal. The patterns and the molds for these parts are, of course, a lot larger than the core. And the surface because there was so much temperature in that mold that they wanted to avoid the sand burning to that surface. So what you can see in the image in a transparent view is the customer worked to actually create some venting pipes all the way through the core in many areas in the vanes. And there's also additional parts that make up the core package. And all of these venting holes align with the next core underneath it or above it in order to direct the gas out of the mold. So that's really supporting that particular customer a lot to reduce those issues. And for the surface finish, we then used a ceramide sand again to help with the sand burn-in and the stability at temperature because it was a steel casting such a large part as well. So these parts are also printed on our biggest machine that we have in our service center. I can show you a little bit about that in a moment. But these would cover let's say the main issues which we see in a couple of examples. Next up, we can take a look at some innovations. So as I say, we covered some of the challenges that we see day to day. And then now I can show you some of the innovations which have happened with the technology and how that's being implemented for some high volume manufacture. So our main innovation project, which we have been working on and realized, is the production 3D printing line to produce a high volume core for BMW. So the project is one which we worked on with Loramendi and Voxeljet for BMW in Germany. And here the vision was to create a 3D printing solution to produce, the goal is 1 million 3D printed cores per year with an accuracy of 0.4 millimeters plus minus, using an inorganic binder to support some environmental topics, and also then to fully automate the process, including the post-processing. And that's one of the main steps, or one of the main steps in this process, which shows a big innovation. As I mentioned earlier in the process slide, to show how the process works, you have to traditionally unpack those sand parts by hand and use compressed air to clean them. So to fully automate that process for a high volume of parts was certainly a challenge. The solution which we defined with Loramendi was to produce a production cell which consists of 5 custom 3D printers which were made specifically for this project. So there are 5 printers, there are microwaves in order to cure the 3D sand printed core after printing, and also robots to handle the parts clean them, and inspect them. So you can see in this image here, you see the 5 red boxes. So these are our printers. And inside the printer, we produce, or inside each printer, we produce 6 cores in every single layer of the machine. And so 6 cores per machine, and these are arriving printed every 20 minutes. So after the printing is complete, the boxes come out of the 3D printer automatically, and they move to a cleaning area where the sand is automatically drained away after the microwave step, and then a robot will pick that core out and do the compressed air cleaning, and then makes a 3D scan of the core in order to check for dimensional accuracy. Today, this production line is in place at the facility in Germany, and it's producing hundreds of thousands of cores per year. So I can show you now what the core looks like, which is produced in the BMW factory. So the part is as you can see, a water jacket core. And it's also including some additional features such as the ports, which are all printed in one single piece. With this 3D printed core and with the help of 3D printing, they can improve the cooling of the engine, reduce the fuel consumption, and then produce a higher efficiency also from the engine. And all of that is made possible through the complex design which was created, which can only be 3D sand printed. And this is quite common for what we see more and more today from end users. More and more designs are being created that challenge the conventional way of manufacture, and therefore 3D printing can offer a really nice solution to address those challenges. So now to jump into some of the technological advancements which we have made. So I can speak today about one example, which is our applications for offshore wind turbines together with GE. And when we speak about these parts in the next few slides, one thing to consider really is that because these wind turbines are offshore, there's a lot of effort and energy in order to get them out to sea, install them, and then also return the energy back to land. And because of that, the turbines need to be really very big in order to justify that effort, which directly translates to large castings that need to be manufactured, transported, and installed. And it's here where 3D printing can really start to support and improve the whole process by being able to, let's say, create a more localized production, reduce the lead times, minimize the labor, and reduce the CO2 footprint, whilst also optimizing on weight of the cast parts. So through the project with GE, they came to us. It was now over 3 years ago, with the idea to manufacture certain components for the wind turbine. You can see here an example of the size of the turbine. So it's 260 meters. Each of the blades are 107 meters. And you can see that there compared to the Tower of Pisa and the Eiffel Tower as well. The main product of focus for Voxeljet in this project is the wind turbine hub. You can see this on the top right, marked in blue. But there are also other cast components, such as this yellow item in the middle, as well as many others. But all of these parts are so large that they have a weight ranging from 30 to 60 tons. So because the effort to manufacture, transport, assemble, and make all of these turbines is so huge, GE came to Voxeljet with the idea to print the molds instead of using traditional methods. And within that, there were a few goals. So the first goal was to optimize the weight. The second was to reduce the effort to move the castings, which means a localized supply. Reduce the assembly effort of the parts. So this would be producing the molds in less pieces versus traditional. And then also to support and improve sourcing of these components. And that's mostly because a lot of these wind turbine components are currently made in China from a few suppliers. Within Europe, there are only a handful of foundries who are capable to produce such large parts, and in the US, around two. So a lot of these are made in China, and of course, bringing such large parts from China to where the turbine installations are has a large cost, and is not necessarily an effective way to approach the task. So as I said, 3 years ago, GE came with this idea, and at that time we started with the first test for 3D printing a mold to create one of the wind turbine hubs. And what we did was we printed this on our VX4000 printer. So this is a sand printer with a build space of 4 meters by 2 meters by 1 meter. And for this test, we had to create a mold which had a total assembled size of 6.5 meters by 6.5 by just over 4 meters. And to give you an idea of how much printing that is, it was 72 different pieces, and it took 6 weeks to print on one of these machines. If you can imagine 4 by 2 meters as a build volume, this takes on the printer just over 2 days. So we made 6 weeks of printing in order to make up all of these 72 individual pieces. The parts were made, sent to GE and cast, and the outcome of the test was very positive. And it produced a casting which was more accurate than a casting made through traditional methods. But one of the kind of clear outcomes was that in order to make this a success for future, and in order to realize GE's vision to have a more localized support and supply chain, we needed to manufacture a larger printer. So GE, one of the main goals within that would be to reduce the printing time down from 6 weeks to 1 week for a complete 3D printed mold. So with that, we got to work and started to, within the project, create a larger printer. So I can show you here the design concept for the printer. And it's actually based on a similar method to our VX4000. But this time the build space, instead of being 4 by 2 meters, is 9 by 7 meters. So we had to create, as you see here, these two bridges. And these bridges are to hold, or one is to hold the print head, which will deliver the binder to the surface, and the other is to hold the recoater, which will apply the sand into the area. But these bridges needed to be very accurate, very strong and stiff, in order to avoid any bending of that bridge, which would have an effect on the quality of the part. So this 7 meter in length bridge has to be very, very robust. So the speed was also important for GE, as I mentioned, to bring down the printing time from 6 weeks to 1 week. And there's two ways which we do that. One is with the bigger platform, and then the other is with a very, very large print head. So on the printing bridge, we'll sit a print head, and that will consist of 7 printing units. And with these 7 printing units, you have just under 60,000 individual nozzles, which will deposit the binder onto the sand. After that, these bridges are controlled by the Z pylons. You see 8 of them in the concept here. And these have to move the entire, or both bridges, which has the sand supply, the recoater, and the print head. It has to move those by 1 layer thickness each time. And on this machine, it moves everything up. So you can imagine how precise these pylons have to be at controlling the whole process in order to accurately move just by 1 layer thickness, a 9 by 7 meter size. So next we can just take a quick look at the impressions from the printer. So here you can see the machine in the facility in Germany. It's currently being built as we speak, and you can see the person standing in front of it there to give you an idea of the size difference. The printer has now been turned on, and the first printing tests will take place in 2025, early 25, and the first casting trial from this printer to be made in February or March next year. After that, the machine is planned to leave and actually go to the US, where the further testing will happen for GE directly, with their vision to produce this production line in future where the 3D printer is just one component, but with the ability to manufacture these huge molds. So we can have a quick look now. It's just a short clip to show you a flyover of the printer. One thing to keep an eye out for is the job box on the right hand side, and this is from the VX4000. So that's the 4 meter by 2 meter, just to show you a comparison with the size of this machine, which is really, really huge. Okay, so with that, that completes just a short presentation for today's webinar, where I hope I can highlight a little bit about 3D sand printing, some of the challenges to consider, and also showcase some of the innovations and advancements which we're making in this space. So if you have any questions, as Angelica mentioned, please feel free to add them into the chat. I'll do my best to answer them, but for any that cannot be answered, please feel free to take note of my email address and mobile, and you can get in touch, and I would be happy to support.
Thank you very much, Cameron. I think we have already got one, let's say, comment. I don't know if you want to read it.
Let's have a look. So I see one question here, which is, I wonder if 3D print manufacturers will eventually separate raw sand and catalyst, introducing the catalyst as a secondary binder during printing. This could leave the residual sand completely loose and easier to remove from the printed parts. The complexity of cleaning is the main reason I hesitate to adopt the technology. Okay, from my experience, this paper print 3D cores, the cleaning remains the most challenging phase. Operate iron casting. Thank you. Okay, yeah, so it's an interesting idea. We have, let's say, different, maybe to explain, we have some different processes which use either the catalyst and the binder, or just a heat activated process. So if you speak about furan printing, which I know is quite well known, let's say in Italy, you do have the raw silica sand pre-mixed with an activator, and then you print the binder. And that means that the residual sand is somewhat sticky after printing. So in the furan process, there's a few things you can do to minimize that effect. Mostly, of course, that is making sure you have good access to the cleaning areas to remove the sand. But it could also be to put the sand or the parts into an oven to dry that unprinted sand a little to help with the cleaning. If you then move to a phenolic binder process, from VoxelJet's side, here we use just the raw silica sand. We print the binder onto the sand, and then we use infrared to cure that layer. And with that, you then have your unprinted sand is dry and loose, and therefore easier to clean. If you think of inorganic sands or inorganic binders, you also need to mix in a catalyst and a promoter, so you still have this pre-mixing. Excuse me. Sorry. So you still have this pre-mixing in the sand. So I would say really a phenolic binder is something which would allow you to have this this dry sand in effect to help with the cleaning. So I see we have another question. So what is the main difference among inorganic and inorganic, and when is it preferred to use inorganic? So we see, let's say, with inorganic binders, a drive towards this from automotive companies, particularly when it comes to environmental reasons. So the inorganic binders produce like an emission-free printed part, which is kinder for the environment versus the furan or phenolic options. Currently, it's only possible to use the inorganics with aluminium castings. So that's where you would see it. Let's say it's a preferred solution in that area, but mainly aluminium and environmental would be the main reasons to utilize that technology. But still today, for voxeljet, and also for other companies globally, the furan printing is still the most common, and it's like the workhorse of 3D printing. So you can really produce high volume. It's a fast process and a cost-effective process as well. Okay, so we have one more question. How much does the post-processing time impact the entire printing process? So the answer would be it depends, and very much depends on what you are printing, and how many parts are in the box and how complex it is. So you might be printing a very small piece where you get 1,000 in the box, or it's just one. But what we often suggest is to take the printed box away from the printer, take that to an unpacking station, and then you would have a second box, which would allow you then to start printing again at the machine, whilst you then go back to the parts and unpack them from that box. And once you've done the unpacking, you can do the final cleaning and compressed air for the post-processing outside of the printed box so that it's ready for the next one. Yeah, I mean, in some cases for the 4x2 meter, we print some very large cores for some customers where maybe only 2 pieces fit. So it might only take 1 or 2 hours or so to remove these parts from the platform and clean everything and put it back. If you have a smaller machine, such as RVX 1000, and only a couple of molds, you could be talking sort of 20 minutes or so to get the parts out. So yeah, very depending on what is in there. But the idea is at least to operate with 2 boxes and be able to print and utilize the equipment whilst you do the unpacking. So your employee can work on the parts whilst the machine is printing the next set of parts. Okay, so
Okay, perfect. I don't see any other question there on the chat. So I think that's all for now. If you have any other question, please write us down, either Camera or me, in the make email. So thank you very much, Cameron, for this webinar.
Thank you for having me.
And thank you everyone who joined. We remind you that we will keep doing next webinars for 2 more sessions, and we wait you all next Wednesday.
Thank you very much.
Thank you very much, everyone.